Thank you very much for the presentation and the invitation. It's a pleasure to be here. Yeah, my name is Angelo Neira. I'm an environmental chemist and a postdoctoral fellow at the University of Constance. My work is focused on soils. So I will start the talk with the question, what is soil? And from a scientific perspective, according to the Soil Science Society of America, soil is a mixture of minerals. You can see the minerals there with different sizes and composition, but soil is also a mixture including organic materials, like those dark circles, air, like those two bubbles, and water surrounding these components. But also soil is the surface layer of the earth that has experienced some degree of weathering, according to this definition, which means some transformation in general. For instance, in the image, you have attractive and repulsive interactions between these soil components, shaping the structure and the reactivity of the soil. So basically, from this definition, we understand soils as dynamic, heterogeneous, and complex systems, but the definition is also a compositional one. We are identifying different components in the soil, and according to their properties and their interaction, we define soil and we predict and measure aspects of soils, which is how science works. In my case, I study soil pollution and specifically the adsorption process. So let's suppose there is a pollutant here. It could be a greenhouse gas, a pesticide, a pharmaceutical, maybe a personal care product, and this access to the soil. And once in the soil water, it interacts with the soil particles. So this interaction is what we call adsorption, and it defines if the pollutant will be adsorbed or fixed in the soil surface, or soluble, which means mobile, bioavailable, and prone to leaching. So we can define mathematically, we can define this KD parameter, which is a distribution coefficient from the adsorbed and soluble forms. And this will tell us if the pollutant is more prone to be fixed or mobile. And we can use this in different contexts. For instance, in the agricultural context, when we are using pesticides, maybe we want pesticides to work effectively, and we need them soluble, so they are bioavailable for the target organism. And then we look for a low KD value. But if we are focused in water pollution and we want to minimize this pollution, we will think of big KD values. So the way we use and interpret this parameter will depend on our objective, the aim, and the experimental design we are using. This is more complicated, obviously. This is just to illustrate the complexity of these contextual aspects in the use of KD. In the literature, we have several kinds of studies showing this. For example, I will show this quick, actually. Yeah. We see 3 different kinds of studies here at the landscape scale and at the macroscopic scale. And you see that in general, when we add organic amendments to the soil, this increases the value of KD. But this increasement is linked at the macroscopic scale in a different experiment to the amount of organic carbon in the soil, which is a component of this soil, according to the previous definition. So we can connect this like more organic amendments imply more organic carbon and then more KD, a higher KD. On the other hand, you have a third kind of experiment studying the soil profile and finding that the organic carbon content decreases with the soil depth, and therefore the KD also decreases. So we are combining these different sources of evidence to produce a general trend, which is we can predict and control these KD values just using the percentage of organic carbon. And this sounds wonderful because we can quantify just one property to support, for example, agricultural management practices. But in reality, this doesn't work in this way. And if we include a new scale, the molecular scale, we will see that all of these different interactions are actually very specific. So the question is, why does this trend work if this is so difficult, actually, so complicated? And one explanation is selection bias. In general, when we study adsorption, we are studying a, a subset of combinations of pollutants, in general, non-ionizable pesticides, adsorbed in agricultural soils that are a very specific kind of soil. So we have an overrepresentation of a subset of pollutant soil combinations, and this makes us believe that this is a generalizable trend when it is not. And we observe the same problem when we use predictive models. For example, let's say we want to predict the KD value of those 3 herbicides. Here we have several approaches. The 2 approaches that are more used in the literature are the quantitative structure activity relationship models. And here the assumption is that adsorption depends exclusively on the physicochemical properties of pollutants. It doesn't depend on the soil. So if you see these chemical structures there, you will see that there are some tiny differences. So if I have a data set, a diverse data set with different molecules, then I can check which part of the molecule is producing a change in the KD, and I can predict the KD of these new molecules. So absorption is generalizable across soils. But there is another perspective, the pedotransfer functions, that says the opposite. Adsorption is soil-specific and depends on environmental and methodological conditions. For example, the acidity of the soil water or the soil solution ratio, properties that you can modify when you conduct the study. So adsorption is complex, it is not generalizable, and you have to analyze it case by case. Now, if we were decision makers, we could say both models are scientifically validated, but one of them has a broader applicability, which is QSAR. You can use it across soils. So probably QSAR is more interesting from a decision-making perspective. And actually, the Organization for Economic Cooperation and Development promotes the use of QSAR models. But the problem with this broader application is we have implicit conditions, restrictions to make it work. And here we need equivalent methodological conditions, but also an adsorption related to one specific subset of combinations, which is these neutral or non-ionizable pollutants adsorbed into the organic carbon content. The same case that is overrepresented in the literature. So the selection of this QSAR is related again with this oversimplification of the complexity of soils that gives us the illusion of a global predictability, while we have decision makers that need control. The QSAR offers apparently this control, and certainty, scientific evidence, both are part of that. So I asked myself how much information we are losing probably due to this oversimplification of soils. And I started to read different articles focused on other interpretations of soils. And this is a book, a very interesting book. Here is a quote by Wendell Berry, who is a writer, farmer, and environmental activist. And he defines soils in a completely different way. He says that the soil is the great connector of lives, the source and destination of all, the healer, restorer, resurrector, by which diseases passes into health, age into youth, death into life. So according to this definition, we cannot extract components, material components, to describe soils. And we cannot measure this definition, these aspects, to predict what soil is. So this is more spiritual or relational. And then I thought in the literature, I'm not the only one who has detected these problems, these issues with overrepresentations of some subsets. But we are still using that approach. And over again, we are doing the same mistake. So the problem is why? I'm not focusing now in how we oversimplify soils, but why we are oversimplifying these soils. And I started to analyze the history of soil sciences to understand if there is a problem in how we inherit the idea of soils. or maybe this is a scientific issue. What is happening here? And then I found this example. This is from medieval history. Here you see a calendar. This is like a manuscript called Treurich Heures du Duc de Berry. And here you see the seasonal rhythms of the rural life. So at the top, you have the zodiac signs representing a cosmic order. This is God's creation, and according to this worldview, God has a plan for us, and we all share a purpose, and all in this creation have its own purpose. Then at the middle, you have castles, and there you have the kings and nobles who act as intermediaries between the cosmic order, between God and the earth. So they own the land, but this ownership is granted by God according to this God's plan. And finally, at the bottom, we have the peasants who work the land. We are not the owners, but we have these ancestral obligations to the land through generations. And the soil here is not sacred, but is part of a sacred rhythm. So the soil cannot be simplified to just material components. It has a connection, a divine connection with God, in the sense that we need the soil to survive. And without the soil, even the king will die, and the whole plan, the God's plan, will collapse. Then we inherited this view, but we removed the divine aspects. So we have a secularization and rationalization process from this pyramid with this hierarchy, and we have a new interpretation of the same hierarchy without God in it. So instead of God, we now have sovereignty with constitutions, abstract norms that explain or define who owns the land. Then instead of kings and nobles, we have now owners, for example, states, markets, corporations, that claim this ownership of the land, but according to the sovereignty. Instead of God, now it is granted by sovereignty. Now, instead of peasants, we have users, different kinds of users. And nature, the soil in our context, is a commodified version now. Now the soil is a measurable resource. It doesn't have these divine parts on it. And this is the origin of science. We can take the material aspects of nature without the divinity on it and measure that to use it. And the soil science history is full of these examples. Here we have 4 different historical shifts. For example, during the agrarian capitalism and colonial expansion, soil sciences were focused in crop yield studies to produce more food, maximize food production, and we did maximize profit. But then, according to the framework of soil productivity. But then with the Green Revolution, the use of pesticides, we faced environmental issues, pollution, degradation, and instead of maximizing, the framework changed to optimize. We have now trade-offs, and we need to increase yields, but decreasing the pollution and degradation. So instead of productivity, now we are using physicochemical parameters and talk about quality. But then there was the institutionalization of sustainability frameworks, the new concepts like ecosystem services, this idea of biological aspects of soils and nature that allow the nature to evolve, to adapt. And then the framework changed again, now to soil health by including these biological parameters. And considering the previous pollution, we are now focusing this in restoring or maintaining the soils to ensure the productivity. And nowadays, we are facing global crises, for example, the climate change or the biodiversity loss. We need planetary governance, and we are reframing soil as soil security, and we consider soil now as a critical infrastructure that we must protect to ensure its utility in a long term. So in all these scenarios, soil sciences has been part of economic changes, or political structures, cultural perspectives, and soil sciences have shaped some of these perspectives, and those perspectives have also shaped what we make a soil scientist. This is also visible in the sustainability frameworks. For example, I'm keeping here the same pyramid to show you how the sustainability model is based, inspired in this pyramid. We have three components: economic growth connected with the part of the owners, social welfare related to users, environmental protection related to this nature as a measurable resource. So we see three different components. They are interconnected, but have some separated aspects as well. And this makes complicated to address some issues that are intertwined. Here I want to share with you one article. The first one, which is pink. I don't know if you can see the difference, but the first one is pink. The significance of soils and soil science towards realization of the United Nations Sustainable Development Goals. That article has more than 2,000 citations, and it is one of the most relevant articles connecting soil sciences with sustainability. And I took three quotes from it to see if this reflects the same structure. And one of these quotes says, for example, that the sustainability depends on the wise use of natural resources. So we are considering this wise part is scientific. So we need to use science to optimize this. And resources are framed as, the nature is framed as a resource. But then they talk about pollution, but pollution is important when it harms ecosystems as economic and social resources for the people. So pollution itself is not relevant. The problem is when pollution affects social and economic aspects of this model. So environmental protection is less relevant than social welfare and economic growth. And even in some cases, we can make the soil no longer a needed resource for the landowner. So the soil is a replaceable resource to be used for human benefit, according to this framework, which is connected with that perspective. And I have another article here criticizing this perspective from an extractivistic approach. And they say that this perspective in particular is based in perceiving the nature not as a living being, but as an inert thing without purposes or meanings, so we can masterize it as we want. And this problem of removing these other layers of complexity from nature is a way to relate with nature. So this is a relational issue between humans and soils. And this produces a tension because these sustainable development goals aim to protect soils, but they are actually protecting the services that soils provide, not the soils. So from this perspective, I try to, again, answer this, what is soil, but now from a different perspective, a broader perspective. And soil is polysemic. It has several definitions, but it is also situated. It depends on the historical context. And you cannot define soils with a single discourse. We need several perspectives of soils. And actually, soils are acting as mirrors of our culture and societies. So there is an example several examples from indigenous knowledge, actually, but I put here one from the Mexica cosmology. This is a god, Tezcatlipoca, which is very complicated to understand in the image. This god represents nature, but the idea in Mexica cosmology is that nature is inaccessible for humans. We cannot understand nature. Nature is complicated, is chaotic, and Tezcatlipoca means smoking mirror. When we try to understand nature, what we are doing is to look ourselves in a mirror, blurred by this smoke, because we can never see beyond our own beliefs and biases. Here I'm using this metaphor because it fits with the idea of soils as polysemic and situated entities. And the proposal is that if we want to understand better soils, not fully, but better, we need different mirrors and worldviews to address what soil is. So my approach is to move from this functional ontology into a relational ontology. And here you have several approaches to do this. My approach is to connect the strong sustainability model, which recognizes this interdependence between environment, society, and economy, and with a body territory lens, which is a decolonial, feminist, indigenous perspective that represents soils as a physical, social, and symbolic space at the same time, in which people build their identity, community, and belonging. So the soil is part of our culture, our identity. And then I propose this redefinition of soil pollution based on this new framework, which is material and symbolic disruption of soil's capacity to sustain, relate, and remember, those three aspects related with the spaces the soil represents, according to the body territory lens. Sustain is material disruption. This is the conventional perspective of soils. There's physical, chemical, and biological contaminants impacting soil properties. This is the classic way we study soil pollution from chemistry, for example. But then we have the relate layer, which is a relational disruption. For example, through this oversimplification of our interaction with soils, we are promoting extractivist and colonial practices and perpetuating them. So this is a relational problem affecting the capacity of soils to relate with us. And then we have the remember part, which is the systemic degradation that can be long-term, cumulative, can be reversible, for example, erosion or loss of function, that is a transformation based on these material and relational disruptions, and therefore with an ecosystemic and sociocultural perspective. It involves everything. So now soil pollution is not a technical scientific problem. It is a relational rupture. And from this perspective, soil is alive and bears the consequences of these unbalanced human actions. So as scientists, we should consider these other aspects. I think we probably already do this. For example, I, as an environmental chemist, analyze this material disruption, while maybe some anthropologist is addressing the relational disruption, but we are not connecting both. So the idea is to connect everything to understand why we are doing this. And I would like to finish with this example of how to make these connections. This is a collaboration between the Maths Academy and the Zukunftskolleg called Making the Invisible Visible. This was a course we made with 5 students creating virtual reality experiences. They addressed this question of what is soil, but from a scientific, cultural, and affective perspective. So I will show you the first of those 2 examples because of time. And the first project was called Soil in Many Different Ways. And here you have 4 landscapes. You have this beach, the mountain, a desert, and a farmland. And the idea was to check how the soil profiles change depending on the landscape and make these differences obvious in soil structure, color, texture, biological activity, etc. So this is a compositional approach, but then you can understand the relational approaches in the land at the surface. So for example, if we analyze the farmland, we could connect these soil layers with the land use and say, okay, this soil is a resource. We have crops there. This is a supplier of these resources. So we are using the soil to survive. Completely functional. So it has a function. But this function can be cultural. For example, if this is a vineyard, maybe we are cultivating some grapes, and those grapes are used to produce wine, and the wine has a cultural value, promotes tourism, etc. So the soil is also a cultural object. But we can reframe this and see it from a relational ontology. So for example, what if instead of resources, the crops are gifts? Maybe we are protecting the soil is rewarding us with gifts. So we feel comfortable with this soil and we continue protecting it, and we feel the crops are part of his retribution. It's a protection for us. So in that perspective, the soil behaves as a mother or a gift giver. And several indigenous people have this perspective and even ceremonies for this interpretation of soils as part of the community. But not only in indigenous perspectives, soil is also a cultural subject in the mestizo traditions, for example. Here in this painting, you see a farmer. His lifestyle is linked to the soil. The soil is constantly changing because of the use of this soil in particular, but this use is part of the life of the farmer, so they are interconnected. And this is reflected actually in the Chilean music. Here you have an example from a fragment of the song El Arado by Víctor Jara. And here you see this idea of the interconnection between the person working the land and the land. So it says, sweat makes furrows in me, but I also make furrows in the soil. And this is something intergenerational. So we are cohabiting the place, we are co-experiencing something, and we could be also co-sufferers in the process. So this is a scientific connection that explains the soil profile, the composition. We can use it to explain functions of the soil, but also how we relate to the soil at the same time. So I have another example, but I will stop now. And the summary of this is the soil is conceptually complex and situated. This affects how we study soils. Decisions rely on this scientific evidence, but this scientific evidence depends at the same time in the lens we use. So better decisions requires a new corpus of knowledge able to include this diversity, this complexity, and to go beyond these situated interpretations. And my proposal is to reframe soil pollution through this relational approach, to enhance this application and rigor of scientific knowledge, to promote socially meaningful and ethically grounded insights, especially for decision-making processes. Thank you very much.